Welcome back, ChemStars. It's time to go over your Chapter 9 homework on limiting reactants. If you're in Level 2 Chem, this is your page 7. If you're in Level 1 Chem, this corresponds to your page 14. Let's look at the objective. Remember, you should have already done this homework, and now we're just checking your work and going over explanations. The objective is, I can use a balanced chemical equation to determine the limiting reactant, that's what you run out of, and to also determine the amount of product made, so how much stuff we can make. This is what people in industry care about when they're doing industrial chemical reactions. Okay, number 1, given 6 molecules of H2, 1, 2, 3, 4, 5, 6, so there's 6 molecules of H2, and 4 molecules of O2, 1, 2, 3, 4 molecules of O2, to form water. We're going to draw a picture. So here's my picture. I've already counted out all my reactants. I've balanced the chemical equation. Now, how much water can I make? Let's just kind of go through and cross these things off. So I've used 1, 2, 3, 4, 5, 6 oxygens. 1, 2, 3, 4, 5, 6 oxygen. And then I've used 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 2, 4, 6, 8, 10, 12. I have used up all of my hydrogen, but there are 2 oxygens left over. And if you can hear that, that is Pickles barking in the background. He is upset. I'm going to pause it and try and calm him down. Okay, Pickles got a cookie and now he's happy. So we were just saying that we could make 6 water and that would exactly use up all the hydrogen and leave 1 O2 left. So what reactant is limiting? That's going to be the hydrogen, the H2. Because if you look at our picture, it all got used up. What is in excess? That's the oxygen. Why? Because there's some leftovers. How many molecules of excess reactant are there? There is 1 molecule of O2 left over. That's supposed to say molecule. Okay, that's looking at it pictorially. Let's look at it now just using the numbers and the BCA table. So what I showed in pictures here, I also did using the BCA table. So we've got our balanced equation recipe right here. We started with 6 molecules of H2 and 4 molecules of O2. And when we look at this, we want to try and guess what we'll run out of. So looking at that balanced recipe, I need twice as much hydrogen as oxygen. So if I use up all 6 of these, I would need exactly how many of these? Twice as much? I would need to have 3, right? So if I had 3 oxygen, I would need exactly 6 of that. I actually have some leftovers, so that's kind of a little mental exercise I did to say, okay, this is going to be limiting. I'm going to use it all up. And then I'm going to use up the coefficient here of the limiting, the thing that I know, times the ratio of the unknown to the known. So I'm using up 3. And I started with 4. 4 minus 3 is 1. There's going to be 1 excess or 1 left over. And how much water did I produce? Well, 6 times the ratio of the unknown water to the known hydrogen. That's 2 over 2. 6 times 2 over 2 is 6 times 1, which is 6. Now, what if you picked wrong? That's okay. What would happen is one of these numbers would come out negative, and that just means, oops, pick the wrong one, go back, pick the other as limiting, and then you can work it out from there. So we're going to label this on top, LR. This is my limiting reactant. And oxygen was my excess. Okay, problem number 2. Here's the ingredients given in this problem. Given 2 molecules of N2 and 8 molecules of H2 to form ammonia. Let's go through and draw a picture like we did on the other problems. So I have my balanced chemical equation. Here are my reactants. Here's the products I'm trying to make. There's 2 molecules of N2. 1, 2. There's 8 molecules of H2. 1, 2, 3, 4, 5, 6, 7, 8 molecules. Now, how much nitrogen, or Ollie, sorry, now Ollie's making sounds. He'll settle down in a second. Okay, so how much ammonia can I make? Well, let's looking at the picture, it looks like we're going to run out of nitrogen first. And here's a little mental math check you can do. I need 3 times as much hydrogen. Here's 4. Do I have 3 times as much hydrogen? Probably. So let's go through and try this. So let's say I'm going to use up all 4 nitrogen atoms. That's 2 N2 molecules. 1, 2, 3, 4. It's going to get me 1, 2, 3, 4. So there I've used up all my nitrogen. We're calling that limiting. And now let's see, if I use up 4 nitrogens, how many hydrogen do I need? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's go over here and cross out 12 with the hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This right here is excess. That's left over. So if I have this much, I will use up all of that. I'll have 4 excess here, and I can make 4 of my ammonia. So how many molecules of NH3 can be produced? I can make 4 molecules theoretically. What is limiting? That's going to be our N2. Why? Because we used it all up when we made the new products. And what is an excess? It's going to be the H2. If we look, there's 4 atoms, but that's really 2 H2 molecules left over. And then let's look at that just from the BCA table without having to draw a picture. Balanced chemical equation. That's the recipe we're going to pull our mole ratios from, and then the ingredients come from the problem. So we've got 2 and 8. Now, if we look at this, we can see that we need 3 times as much hydrogen. Well, okay, let's say if we use up exactly 2 nitrogen, we need 3 times as much. That's 6. Do I have at least 6 hydrogen? Yeah. That means this will be excess. So before the reaction starts, here's what I have. During the reaction, during the change, I'm going to use up all 2 of the nitrogen. There'll be none left over. During the change, I'm going to use up 2 times the ratio of the unknown hydrogen to the known nitrogen. 2 times 3 over 1 is 6. So 8 minus 6 is 2. Before the reaction, there's 8 hydrogen. It will use up 6. There'll be 2 left over. And then for the ammonia, I'm starting with 0. I'm creating 2. The 2 comes from right here, times the mole ratio, which is 2 over 1. 2 times 2 over 1 is 4. Start with 0, create 4. There are 4 left over. If you look, this matches up exactly with this picture. Good. Let's flip the page. Okay, so level 2, page 8. This is the same as level 1, page 15. Little bit more complicated, took away some of the pictures, but it's the same theory. So let's just go through some of these problems together. Remember, you should have attempted them on your own first. Now we're just checking our work. So you have 7 moles of C2H6. That's a hydrocarbon, so it goes right here. That's where this 7 came from. It came from right here, and that's where this 10 came from. And you burn it with 10 moles of O2. First of all, what type of reaction is this? Combustion, where things blow up. And all combustion is a hydrocarbon plus oxygen burning to give us CO2 and water vapor. We're asked to find out the limiting and how many moles of each of the products we can use. So first thing is we have to predict those products, CO2 and H2O, and then balance it. Remember, the easiest way is to balance C, then H, then O last. We have the little trick. We can half balance if we need to. It ended up the ratio is 1 to 3.5 to 2 to 3. Technically, we should double this, but we can do a little cheat here because it's all about the ratio. Now, it's not a whole number ratio. We're going to get the same math. So if some of you have 2, 7, 4, 6, you're going to get the same answer that I get doing it this kind of cheat way. So just stick with me. Let's see what happens here. Okay, when we're looking at it, what do you think we might run out of first? I need 3.5 times as much oxygen as I need the hydrocarbon. So if I'm going to use up all 7 of this, I need 3.5 times as oxygen. That's over 21, less than 28. Do I have at least 21 oxygen? It looks like I'm probably going to use up all the oxygen. So let's try that. Let's say that oxygen is going to be my limiting reactant. It's all going to be used up. Then we're going to calculate everything else off of that oxygen number. So we're going to be using up 10 times the ratio, the mole ratio, 10 times 1 over 3.5. Now let's use our calculator. Okay, where is my calculator? Let's find that. Here's my calculator. So we're taking, let's see, what were we taking here? We're taking 10 divided by 3.5. So 10 divided by 3.5, and we get 2.86, let's say. So this number right here is 2.86. Now look at it. We started 2.86. We started with 7. We're only using up 2.86. We're going to be okay. So let's take 7 minus 2.86, and we're going to have 4.14 left over, or 4.14 moles excess. Good, that means we chose wisely. If we got a negative number here, it means we would have chosen poorly. So how much CO2 can I make? We can make 10 times the ratio. Now, the ratio, oops, I used the wrong color. Don't want to confuse you with my color code in here. We're going to create 10 times the mole ratio. So this is going to be 10 times 2 over 3.5. So let's try that. 2 divided by 3.5 times 10, 5.71. We're going to be creating 5.71 moles of the CO2. And how much water will we make? We're going to be creating 10 times the mole ratio of the unknown water to the known oxygen. We can leave that as a 3.5 times 3. So 10 times 3 over 3 from right here, and 3.5 from here. 10 times 3 over 3.5. So 3 divided by 3.5 times 10, 8.57. So I just created 8.57 moles of H2O. So what was limiting in this problem? It was oxygen. And then their final answer right here. So this answer comes right here. Okay? Oh, and that's supposed to be CO2. A little crooked. Okay, we got 2 more problems before we're done. Number 4. Let's look at this one. This one says you have 0.5 moles of calcium hydroxide and reacts with 0.6 moles of HCl. This is a double replacement reaction, and I'm going to plug in these numbers. These are the ingredients from the problem. Remember, the balanced chemical equation, that's where we're getting the mole ratio recipes. One other note, specifically this is an acid-base reaction, which we'll study more in chapters 14 and 15. So let's just kind of take a look at this real quick. Let's pick the limiting reactant together. I need twice as much HCl as I need the calcium hydroxide. So to use up all of this, I need twice as much. 0.5 times 2 is 1. Do I have 1 HCl? No. That means that I'm probably going to run out of the HCl. So let's work under that assumption. So if I have 0.6 and I use up 0.6, there'll be none left over. How much calcium hydroxide will I use up then? I'm going to use up that 0.6 times the ratio of the unknown calcium hydroxide to the known HCl. Okay, so we need to kind of figure out what this is. Deuce in your head. What's half of 0.6? 0.3. 0.5 minus 0.3, there's going to be 0.2 moles excess left over. So right now we know for sure that HCl is limiting, and then that there's going to be 0.2 moles of excess calcium hydroxide left over. We're not done because they do want to know how many moles of each product can be made, which we're going to solve for right over here. So let's solve for that. We're going to be creating, we start with nothing. Before I make brownies, I don't have brownies, remember, so I'm starting with 0 calcium chloride, and I'm going to be creating 0.6 times the ratio of the calcium chloride, the 1 to the 2, the unknown to the known. We already said that this term we know is going to be 0.3, so I started with 0, I created 0.3, I'm going to have 0.3 moles of my calcium chloride created from this reaction. Now let's try the same thing with the water. So we're going to be creating the 0.6 because I'm going off my limiting reactant, that's the ingredient I'm running out of. The ratio of the unknown water is 2 to the known HCl is 2, so 0.6 times 2 over 2, that's 0.6 times 1. So I've created 0.6 moles of H2O. Good, that's that problem finished. And we got one last one. Thanks for sticking with me, we're almost done. So let's look at the problem here. 3.5 moles of lead-2 nitrate reacts with 2.80 moles of sodium iodide. These are my ingredients. It's a type of double replacement reaction. Go back to your chapter 8 notes if you need more help balancing and predicting. They want to know how many moles of each product are made. Okay. So let's just take a look here. 3.50, 2.8. Now, looking at this, we need twice as much sodium iodide. So if I'm going to use up all 3.5 of the lead nitrate, I'm going to need 7 of this. Do I have 7 of that? Nope. That means I can't use up all this. That implies that sodium iodide is going to be my limiting reactant right here. So let's work under that assumption. So before the reaction, here's what I have. This much from the problem, no products. No brownies until you make your brownies. So after the reaction, after the change, we have none of that left. How much of the lead nitrate? We do have to do this step to make sure we pick the limiting reactant right. So I'm going to be subtracting 2.80 times the mole ratio, which I'm pulling from that balanced chemical equation. So 1 to 2. So what is this number? What's half of 2.8? Well, that's going to be 1.4. So if I started with 3.5 and I'm using up 1.4, there's going to be 2.1 excess. That means good. I picked the right thing. It's a positive number. If it had been negative, we would have picked the wrong one, have to start over. Okay, now we have to figure out how many moles of each product are made. How do we solve for that? Right here. Okay, so everything's based off of that limiting reactant. So that 2.8, now we're going to take the unknown to the known. So 1 lead-2 iodide for every 2 sodium iodide. What is this number? Well, we already did that. It's 1.4. If I started with 0 and made 1.4, that means after the reaction, I'm going to have 1.4 moles of that lead 2 iodide. Now, how did I know it was lead 2? Well, in the beginning, they told us it was lead 2 nitrate. Just always assume if you have a transition metal, it'll be the same charge the whole way through the problem. And one last one, we've got to get the sodium nitrate. Okay, so we're going to be creating 2.8 times the mole ratio. And on this one, my mole ratio is 2/2, which is 1. So 2.8 times 1 is 1. If I started with none, and this whole term, this is just 2.8, that means I'm going to have 2.8 moles of the sodium nitrate when I'm done. Thanks for sticking with me, guys. Have a great day. Bye.